So let's look at another example. So this question is, what type of bond exists between carbon-oxygen atoms in CH2O? Single, double, or bond? Double, etc. Okay, so when we draw the molecule, let's look at it. We can already looking at the answer, we can see a couple different things. Now, if you want to, I really recommend you stopping the video, working this out before I actually go over the answer. So you can see that even before we draw anything, okay, we know a few things. One, carbon has a valence electron of 4. It has 4 vacancies, so it can fit 4 things around it. There are 1, 2, 3 things bonded to it. Okay. What do you think that means? So, looking at D, it says there is no bond between carbon and oxygen because the oxygen is bonded to the hydrogen. Okay. Notice hydrogen has 2 bonds associated with it. Okay. Hydrogen never double bonds. There's no 2 bonds for hydrogen. So you can already say D is not the answer. If we draw it, we can see, looking at the valence electrons, okay, carbon is in the center. You have 1 hydrogen, 1 hydrogen, 1 oxygen. We know that oxygen likes 2 bonds. We know that carbon likes 4 bonds. So we can put together that oxygen has areas, 2 electrons that it can bring over and share with carbon. That means oxygen has 2 bonds, carbon has 1, 2, 3, 4, and then the hydrogens all have their singular bond. Okay. So we can characterize these bonds in different ways. Now we talked about a few different things. We talked about drawing the Lewis structure. We can talk about calculating the formal charges, resonance energy, and things like that. We briefly covered that in resonance energy, the bond length shortens. What do you think that means? So besides thinking about it in the sense where we have 2 atoms closer together, okay, we can think about it in bond energies too. So the bond length is the distance between 2 nuclei. Okay. So you might see this as the summation of the radius of the nuclei of A plus B. So depending on how big A is, depending on how B is, there is an overlap that is associated, just like when we talked about the 2 hydrogen atoms, right? You put 2 hydrogens together, you can only get so close, right? So as the number of bonds between 2 atoms increase, the bond grows stronger, okay, and shorter. So a single bond, okay, so if you look at just having 2 nitrogens with a single bond, that can be 1.47 angstroms. And remember, what chapter was that? Chapter 6, maybe chapter 2, we talked about angstroms. So you can go back and refer to that. We're just basically saying, look at the length. You have 1.47 with a single bond, and as you go from a double bond to a triple bond, that length shortens. Okay, so it gets shorter and shorter as the number of the bonds increase. That also, if you think about it, increases the strength. So if you have 1 stick, 1 long stick is easier to break than 3 short sticks, right? So we describe the strength of the bond by the bond energy. Okay? It is the amount of energy released when a bond formed. Okay? So decreasing potential energy. And remember back in chapter 1 we talked about different types of energy. We talked about potential, which is what we're saying is stored energy. So we have energy stored between these bonds. We have kinetic energy when we talk about thermal energy. So right now we're focusing a little bit more on and getting more into detail about the potential. We talked a little bit more about kinetics in chapter 6. Now is the time to talk about the stored energy. And in chemistry, we call that chemical bonds. Okay, it's the amount of energy that must be put in to break a bond. So remember a few weeks ago we talked about what's actually happening, reactions. You come with a compound that has these interactions. Some energy must be put into the system, or it could just be that the element of one molecule prefers to interact with the element of the other. You have dissociation. Okay, so the energy to break these bonds, okay, it's called the bond energy. The larger amount of energy equals a stronger bond. So you have to put a lot more energy into breaking 3 short bonds, those 3 short sticks, than you do for 1 stick, right? So I don't know if you guys played around with breaking sticks for kindling or for campfires, right? If you have 1 stick, you can easily break it over your knee. If you have shorter sticks, they're harder to break. If you have multiple short sticks, they're even harder, okay? So think about that when you're talking about bonds. So there we go. Potential energy. Again, this is the stored energy. Potential energy, we saw examples in chapter 1 from gravity. We talked about the car going over. We could talk about springs, positive, negative charges. And chemical energy. So potential energy is possessed by chemicals and stored as bonds. Breaking bonds require energy. So you have to put energy into the system to break bonds. Forming bond releases energy. And so remember when we said that negative means bonds are, negative energy, the lower the energy, the more stable it is. Okay. Positive energy means that you have to put energy into the system. You have to bring in energy and break bonds. When you form bonds, that is energetically favorable and it releases energy. So here is just rewording of what I just said. Forming bonds, breaking bonds. Forming bonds releases energy. Breaking bonds require energy. So the atoms, another way to think about it is the atoms that are together are attracted. You're already together. So if you had a good friendship, right, it would take a lot to break that apart. Okay? It takes a lot of energy to break that apart. When you're forming bonds, you can think about if you click with someone, right? That doesn't require a lot of energy. You click, you get together, you react and do things, right? That's kind of a weak analogy, but that's one from the top of my head. We measure this energy through enthalpy. So enthalpy, delta H, is the heat content of the system. And we'll talk more about this in chapter 5 and chapter 9. But we have mentioned this when we talked about trends. When we talked about energy being released is called an exothermic process. When heat is absorbed or intaked is called endothermic. So we can say when heat is released, okay, this is more energetically favorable. So we have a negative value. So more negative, more stable. When energy is put in, endothermic, delta H is positive. So endo, exo, like you breathe out, you get rid of your X's, if that's one way to think about it. So exothermic is negative, endothermic is positive. So in this case, when energy is released, when forming bonds, you can say that's an exothermic process. Breaking bonds require energy, and it's an endothermic process. And we can see a table in your book, table 8.3. You do not have to memorize this table. You can just notice the trends. So bond enthalpies are positive because breaking bonds is an endothermic process. Okay. These are averages over many compounds. Not every bond for a pair of the atoms will have the same bond energy. So just because one carbon hydrogen is 413 doesn't mean all carbon hydrogens are 413 kilojoules per mole. This is an average between multiple different kinds of compounds that have a carbon hydrogen single bond. So you can see that all these energy values are positive. Again, endothermic process. And we'll learn how to calculate and predict reactions based on the bond enthalpy in chapters 5 and a little bit in 19. Okay. But in general, let's look at, where's carbon? Carbon and carbon, carbon and so carbon, 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 and carbon. So you can see that the bond energy of a single bond is between two carbons is 348. That increases as you increase the number of bonds. So if you have a triple bond between these two carbons, it requires 838 kilojoules per mole, where only one single bond has less than half of the energy required. So it requires more energy to break multiple bonds. So we can relate the energy and the length. So as the length gets longer, the energy required to break the bonds decreases. So as you increase the number of bonds, it shortens. Not only does it shorten, it will also increase the energetics. So multiple bonds are stronger than single bonds. As the number of bonds between two atoms increase, the bond length decreases. Okay, so as you increase the number of bonds, the distance between the two atoms decreases, so they get closer together and it's harder to break them apart. Shifting gears just a bit, we can look at these bonds and describe them not only by energy and length, but what we are going to call polarity. So bond polarity. Now we've all been talking about covalent bonds. However, and this is kind of getting to chapter 9, okay, we can see that when we have two covalent bonds, okay, or two atoms that are covalently bonding, they're sharing electrons, but that doesn't necessarily mean they're sharing equally. Okay. So, if you look up sharing for images, it's mostly a lot of animals. There's not a lot of kids sharing equally. If you have kids, that's probably a bit more realistic. I don't have kids. I don't even have guinea pigs. But you can see that these two lovely animals are sharing a carrot. They're sharing equally. Okay? These kids are not. They have a toy. This kid has the majority of the toy. This kid has only the top of it. So while they're both playing with the same toy, one is getting a lot more out of it than the other. And we call that polarity. So if you think about the North Poles, right? There's two poles. There's a positive end and a negative end. Okay? You still have sharing going on. Okay? Electrons are still being shared, but they're not being shared equally. So with a nonpolar, okay, nonpolar covalent bonds, the electrons are shared equally. Polar, however, because there is a pole, one of the atoms exerts a greater attraction for the electrons than the other. Okay. So my other analogy is a chocolate bar. Okay. I have siblings. I don't know how many of you guys have siblings, but when your mother tells you to share your chocolate bar, there are two types of siblings. There's the one that would break the chocolate bar in half and give the sibling half of it. And then there's more like me, where when my mom tells me to share, I'll share. They get maybe the first row of the Hershey bar. They still get chocolate, just not as much as they expect, right? So we'll pick this up in the next video.